Good evening, dear students. So let us continue our class on matrices in continuation of wherever we concluded in our last class. If you recall, dear students, in the last class we concluded with the matrix multiplication. You can always look into my YouTube videos. I made it available. You can look into till matrix multiplication. If any one of you missed the class, or if anyone wants to go through once more, please have a look into it. So now what I'm going to discuss is about the transpose of a matrix. So what is transpose? It is a new terminology, and let us understand what is that. Dear students, suppose we have a matrix of order m by n. That means it has m rows and n columns. Now, what we are going to do is that suppose we have a matrix of order m by n. We have a matrix A of order m by n. That means what? It has m rows and n columns. Now, what we are going to do, we are interchanging the rows and columns. That means whatever the rows are become columns, and whatever the columns become rows. Then whatever the new matrix what I am going to get, okay, that is going to be a transpose of that matrix, and obviously the transpose will have n number of rows and m number of columns, and that is generally denoted by A prime. A prime, it is denoted by, or it is denoted by A transpose. So as you see that A transpose or A prime, so what I can write is that this as order n by m, it will have n number of rows and m number of columns. That is also same as A transpose. That is also equal to, we can write is that A transpose. It has n number of rows and m number of columns. When we know that the matrix A is having m number of rows and n number of columns. Let's take an example first. Before I define, let's take an example. Because as you know, dear students, if we take example, things become well understood. So if you look into here, that matrix A, what we get, the matrix A is having 3 rows and 2 columns. You see, it has 3 rows. This is the first row. First row elements are 1, 2. Second row elements are 4, 5. And third row elements are 7, 8. And how many columns it is having? It has 2 columns. First column elements are 1, 4, 7. And second column elements are 2, 5, 8. Now, in the transpose matrix, dear students, what is happening is that the row become column. That means whatever the row 1, 2, that becomes the column. This was the row, that 1, 2, that becomes a new column. That becomes the new column, first column. Second row in the original matrix 4, 5 becomes the second column of the transpose matrix. Third row in the original matrix, that is 7, 8, becomes the third column in the transpose matrix. And obviously it is the other way also. If you look into the first column of the original matrix, which is 1, 4, 7, becomes the first row of the transpose matrix. And the second column of the original matrix becomes the second row of the transpose matrix. So in the matrix A, what we are seeing is that we see that there are 3 rows and 2 columns, 3 by 2. Then in the transpose matrix, what we see, it has 2 rows and 3 columns, 2 by 3. So now let's come to the formal definition of transpose of a matrix. So what is that? That let me show you the formal definition, and then we will look into some of the properties of the transpose of a matrix. So let A be a matrix of order m by n. Then the transpose of the matrix A, denoted by A prime or A power t, means whatever the way you want to denote, will be obtained by interchanging the rows and columns of the matrix A, whatever we have seen in the example. So this is all about the transpose of a matrix. Now, dear students, the transpose of a matrix has some interesting properties, and that we are going to learn now. So what is that? Now, first thing is that if you see that, let me first, keep the note here and then we'll discuss. So the second property, actually it is the first property. First one is the definition. Then its property is that if the order of the matrix A is m by n, then the order of the matrix A prime, that is the transpose of A, is n by m. And obviously, dear student, if you transpose the transpose of a matrix, you get the original matrix, isn't it? You see, here what we get, we can take an example of this one. If you see that in this matrix A prime, we get that 147258. Now let's make a prime of A prime. So this implies what A prime of prime. What we are going to get? So as the A prime is having 2 by 3, means 2 rows and 3 columns, so A prime of prime will have 3 rows and 2 columns. So the first row becomes the the first column of the A prime prime. That is, first row is what? 147 of A prime. So A prime prime should be 147 will be the first column. And what is the second row of A prime? It is 258. That will become the second column of the A prime prime. That is 258. Now, if you look at, dear students, what you'll find that 147258, that column wise what I read, is actually exactly equal to the matrix A. So what you can conclude, A prime prime is equal to A. That way, or I can say transpose of the transpose of a matrix is the original matrix itself, and that is the second property. Third property is that, dear students, is that K of A transpose. That means if each and every element of the matrix A is multiplied by K, it is as if that you first take a transpose of the original matrix A and multiply that element K, where K is a real number. Third, the next property what we see is that A plus B transpose is equal to A transpose plus B transpose. And the last one is very important, but there is a little difference here, is that A into B transpose is equal to B transpose into A transpose. A into B transpose is equal to B transpose into A transpose. So let's have a look into all these things by means of an example. Okay. And when I'm getting that example, you also work with me. You can also work with me to understand that how we are going to find it out. Okay. So let us take especially the last property. Last property is very important to understand, that how come AB transpose is equal to B transpose into A transpose. So let us take two matrices, dear students. The first matrix is A and second matrix is B. Let me show you these two matrices here. As you see, these two matrices, A is a 3 by 1 matrix and B is a 1 by 3 matrix. Now, why it is so? Because in order to have A into B defined, dear students, if you recall, in the last class we have discussed the number of columns of the matrix A has to be equal to the number of rows of the matrix B in order to have A into B defined. Correct or not? So what we see, this matrix A is having 3 rows and 1 column. And the matrix B is having 1 row and 3 columns. So then A into B, that is AB, will have 3 rows and 3 columns. So let's find it out how we are going to find that matrix A into B. And then we will do what? First we will do A into B transpose. We'll get one matrix. Then we'll do B transpose and A transpose and then multiply them. Then we'll see what we are going to get. So first what we're going to do, dear students, is that first we are going to find the value of AB. So if we want to find the value of AB, just let me write it down. It is -2, 4, and 5. You can also do it along with me. You can open your notebook and you can also do the way I am doing. And the second matrix B is that 1, 3, -6. Now, if you recall, dear student, that the way I explained you the other day, the matrix multiplication, how it happens, I'll go for the matrix A in the row wise and come down for the matrix B in the column wise. So how we are going to get this matrix multiplication? So here it is. So this will become, -2 into 1, that is -2. Then -2 into 3, that is -6. Then -2 into -6, that is 12. The second one is that 4 into 1, then the second row elements, I'm going to find it out of the product matrix AB. 4 into 1 is 4, then 4 into 3 is 12, and then 4 into 6 is -24. So 4, 12, -24. Correct, no, dear students? Then we are going to find the third row of the matrix, resultant matrix. So 5 into 1, that is 5. 5 into 3 is 15. Then 5 into -6, that is -30. So this is the matrix what we get as A into B. Now what is our target? Our target is to find the matrix A into B transpose. So if this is equal to AB, then what will be A into B transpose? It is a prime or power T, means the way you want to write. It will be a 3 by 3 matrix, but the row and column will get interchanged. That means whatever the row in the matrix AB will become the column in the matrix AB. So what is the first row? It is -2, -6, 12. If you look into the first row, dear students, so this is the first row. So that will become the first column. So what will be the first column then? It will be -2, -6, and 12. What is the second row? Second row is this one, 4, 12, -24, and that will become the second column of the transpose matrix, that is 4, 12, -24. What is the third matrix, third row, dear students? Third row is that 5, 15, and -30, and that will become the third column of the resultant matrix. So what it will be? 5, 15, and -30. So if you look into this, so we get that A into B transpose is something like this. So we give this as equation 1. So let me read row wise. What we get is that A into B transpose, that is -2, 4, 5, -6, 12, 15, and 12, -24, -30. All right. Now, what we are going to do, we are going to establish this property. We are going to just, see that how these properties are working. Now, what we need to do, we need to do B transpose into A transpose. So if this is B, then what will be B transpose, dear students? So B transpose into A transpose. So B transpose will be the matrix B, as you see, is having 1 row and 3 columns. So B transpose will have 3 rows and 1 column. So it will be 1, 3, -6. And dear students, that A transpose is having is 3 rows and 1 column. Sorry, the matrix A is having 3 rows, 1 column. So A transpose will have 1 row and 3 column. What is that 1 row? That is -2, 4, and 5. Now, according to this rule, as you see, according to this rule, if we make this multiplication of two matrices B transpose into A transpose, this we should get as AB transpose, what you see it here. Let's see. Let's find it out. So how to get this thing? So this is equal to, as you know, the way to do it is that as we learned about the matrix multiplication, let me repeat once more, is that for the matrix B transpose, we will go row wise and for the matrix A transpose the column wise. So how to do this thing is that, row wise and column wise, when we are going to multiply, then it becomes something like that. It becomes 1 into -2, that is -2. 1 into 4 is 4, and 1 into 5 is 5. You see, we started saying what about the first row of A into B transpose, that becomes the first row of B transpose A transpose. That means we are in the right track. Second one is the 3 into -2 is -6. 3 into 4 is 12, and 3 into 5 is 15. Then you see -6 into -2, that is 12, and -6 into 4 is -24, and -6 into 5 is -30. So we give this as equation 2. Now, dear students, if we look into both equation 1 and equation 2, what we can conclude? If we look into this equation 1 and equation 2, so equation 1 and equation 2, if you conclude, what we can say is that A into B transpose is equal to B transpose into A transpose. This is an important result. Questions come from here. Never get mixed up is that, with the A plus B transpose. If you see A plus B transpose, that is equal to A transpose plus B transpose, which you see it here. But A into B transpose is equal to B transpose into A transpose. I hope this is absolutely clear. Okay, you understood. Now, dear students, we are going to learn something called symmetric and skew-symmetric matrix. Very important, and we'll see some properties of it, and we'll establish one important, rule. One important statement we can say about that any square matrix, how we can represent, as a symmetric and skew-symmetric matrix with algebraic operations. We'll see this thing in the next, half an hour or so. So the first and foremost thing, dear students, is that, we need to define what is the symmetric and skew-symmetric matrix. Let me go to a new page and let me explain about the symmetric and skew-symmetric matrix. So what is a symmetric and skew-symmetric matrix? So first, let us define what is symmetric matrix. The definition is a matrix is said to be a symmetric matrix if both the following conditions hold true for the matrix A. First one is that the matrix has to be a square matrix. And second thing is that the transpose of that matrix should give you the original matrix. That means A transpose should be equal to A. You may be wondering, sir, how we can say this thing that a matrix, is equal to the its transpose is equal to the same. Let's see it. Okay, then you'll understand. So let us consider a matrix something like this. Okay, let me show it to you, dear students, here. So let's consider a matrix A is something like this, and let us find its transpose. If we want to find the transpose of this matrix, so how we are going to find it out? So this implies A transpose is nothing but interchanging the rows and columns, correct or not? What is the first row? First row of the original matrix is √3, 2, 3. So that first column of A transpose should be √3, 2, 3. So it should be √3, 2, 3. Correct, my dear students? If you look into the what is the second row of the original matrix? Second row of the original matrix is 2, -1.5, -1. So in the transpose matrix, the second column should be 2, -1.5, and -1. And if you look into the third row of the original matrix, third row of the original matrix is 3, -1, 1. So the third column of the transpose matrix would be 3, -1, 1. Now, dear students, look into these two matrices, that A and A transpose. This is the matrix A and this is the matrix A transpose. If you see, both the matrices are exactly same. How come we can say both the matrices are same? Let's go back to the fundamental property of equality of two matrices. When the order of both the matrices are same and the corresponding elements are equal, order of both and A transpose is 3 by 3. And if you see the corresponding elements are same. For example, what is the first row and first column? √3 of the original matrix. What is the first row and first column of the transpose matrix? That is also √3. Let's take arbitrary 1. What is the element in the third row and second column of the original matrix? -1. That is equal to the same element in the transpose matrix in the A transpose, that is in the third row and second column. So we see this matrix, what I give an example, is a classical example of a symmetric matrix. So let me repeat once more, what is symmetric matrix, dear students? A matrix A is said to be symmetric matrix if both the following conditions hold true for the matrix A. First one is that A is a square matrix, and second one is that transpose of that matrix should be equal to the original matrix. That means A transpose should be equal to A. If any of these conditions doesn't hold true, then we can say no, this matrix doesn't qualify to be a symmetric matrix. Now let us come to define the skew-symmetric matrix. So let's see what is a skew-symmetric matrix, and you will find that definition interesting. Okay. So a matrix is said to be a skew-symmetric matrix, if both the following conditions hold true for the matrix A. The first one, dear student, is that A is a square matrix, like the same condition like the symmetric matrix. And the second condition is that A transpose should be equal to -A. First one is that A is a square matrix and A transpose should be equal to the -A. That means in the original matrix, if you multiply each and every element with -1, whatever the matrix you will get, that should be equal to the transpose of that matrix. You may be wondering, sir, okay, how it is possible? Can you give an example? Absolutely. Okay, we can give an example. So let us take an example of a skew-symmetric matrix. Okay, so earlier we take an example of a matrix A. Now let's give an example of a matrix B. Okay, so how it is? So here it is the example. Let's look into this matrix where the matrix B is defined as, it is a 3 by 3 matrix, dear students. And if you see, the first row elements is 0, E, F. Second row elements is that -E, 0, Z. Third row element is -F, -G, 0. Now what we are going to do? We are going to do a transpose of this matrix. And let's see what we are going to get. If we make a transpose of this matrix, dear students, so what we are going to get, B transpose should be row become column. So if we see, the first row become the first column of the transpose matrix. So that means, what is the first row of the original matrix? 0, E, F. So in the transpose matrix, it should be 0, E, F. What is the second row of the original matrix? -E, 0, Z. So what we'll get? We will get the second column of the transpose matrix, that is -E, 0, G. And what we will get? The third row of the original matrix, that is -F, -G, 0. So what will be the element in the third column of the transpose matrix? That should be -F, -G, 0. Now, dear students, so we give this equation as equation 1, that what we get as B transpose. Now, as we know, B is equal to this 0 EF, row wise I am reading 0 EF minus E 0 G minus F minus G 0. What I'm going to do, dear students, I'm just going to multiply each and every element of the matrix B by minus 1. So if B is equal to this, then what we are going to get as that minus B. So minus B is nothing but each and every element will be multiplying with minus 1. So 0 multiplied with minus 1 is 0. E multiplied with minus 1 is minus E. F multiplied with minus 1 is minus F. So 0 minus E minus F. Minus E multiplied with minus 1 is E. Minus E, sorry, 0 multiplied with minus 1 is 0. G multiplied with minus 1 is minus G. Minus F multiplied with minus 1 is F. Minus G multiplied with minus 1 is G. 0 multiplied with minus 1 is 0. Now if you look into it very minutely, dear students, so this is 0. Now if you look into, let's give this as equation 2. Now if you look into both the matrices in the equation 1 and equation 2 minutely, what you can conclude, dear students? If you take this one and this one, we are going to conclude that B transpose is equal to as if minus B, because minus B, whatever the content in the in a minus B is actually the content of B transpose. So B transpose equal to minus B. So what we are going to discuss, what we established is that B transpose equal to minus B. That is a classical example of a skew-symmetric matrix. So dear students, I hope you get a very clear idea about the symmetric and skew-symmetric matrices. Now we are going to discuss about the few properties, few fundamental properties that we can establish. The first one, what we can say is that all diagonal elements of a skew-symmetric matrix are 0. So let's establish that. Okay, and we will establish with our fundamental understanding about the skew-symmetric matrix. What it is saying? It is saying all the diagonal elements of a skew-symmetric matrix are 0. Let's see how it's going to be, true. So we are going to prove it. Together we can prove it. I am doing it, and you see that you will also completely agree with me, because we are discussing, with a proper, methodology, so that everything is very clear to your mind, I hope. If it is not, please do let me know. All the diagonal elements of a skew-symmetric matrix are 0. Let us take a matrix A, and let us take, it is a 3 by 3 matrix. So first element is A11. Second means, first element means the element of the first row is A11, then A12, A13. So I am writing this matrix in row wise. Then A21, A22, and A23. Then A31, A32, A33. If you see, this is the matrix of A. Now let us make a transpose of this matrix. Okay, so as we get A, then what will be the A transpose? A transpose you can write is that A prime, or also let me write a different flavor. You can write in this manner also. Sometime if you get like this, then also you assume this is it is indicating that it is a transpose of the matrix. So what is the transpose of the matrix, dear students? I hope you by this time you are very clear. The row of the original matrix becomes the column of the transpose matrix. What is the row of the original matrix? First row. First row of the original matrix is this A11, A12, A13. So that will be the element of the first column of the transpose matrix. That means A11, A12, and A13. What is the element in the second row of the original matrix? That is A21, A22, A23. So what we are going to get in the transpose matrix second column is exactly the second row of the original matrix. So that means what we are going to get A21, A22, and A23. Now let's look into what is the third row of the original matrix, dear students. It is A31, A32, A33. So then third column of the transpose matrix will be exactly this, that is A31, A32, A33. Correct, no, dear students? Now let's look into it, that is A transpose. So we give this as equation 1. Now, as skew-symmetric matrix, so what A transpose should be equal to minus A. So now let's find first minus A. As you know, A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. So from here we can find what is minus A. Minus A will be what? Each and every element is multiplied with minus 1. That means minus A11, minus A12, minus A13, minus A21, minus A22, minus A23, minus A31, minus A32, minus A33. That is the minus A. So this is equation 2. Now, dear students, what we see is that from the property, the definition, not property, definition of skew-symmetric matrix is that A transpose should be equal to minus A. Okay. Now, as A is a skew-symmetric matrix, so what I can write is that as A is a skew-symmetric matrix, as A is a skew-symmetric matrix, what we are going to get? This implies that A transpose should be equal to minus A. This implies what? From the equation 1, we get what is A transpose. What is that? A11, A21. I'm writing row wise of the A transpose matrix. A31, A12, A22, A32, A13, A23, A33. That should be equal to, minus A. Minus A, we understood from that equation to what? It becomes minus A11, minus A12, minus A13, minus A21, minus A22, minus A23, minus A31, minus A32, minus A33. Now, dear students, let's go back to the fundamental, understanding of equality of two matrices. When two matrices are going to be equal, if you recall, the equality of two matrices means what? Corresponding elements has to be equal. That means this A11, which is in the junction of the first row and first column, should be equal to the minus A11, which is in the junction of the first row and first column of the right hand side matrix. So from here what we can say is that A11 is equal to minus A11. That implies what? That implies 2 into A11 is equal to 0. That implies what? We get A11 equal to 0. Similarly, students, what is in the junction of the second row and the second column of the left hand side matrix? That should be equal to the junction of the second row and second column of the right hand side matrix. So from here what we get, dear students, A22 is equal to minus A22. That implies what? That implies 2 into A22 is equal to 0. This implies A22 is equal to 0. Now, in the similar manner, what is in the junction of the third row and third column of the left-hand side matrix? That should be equal to the element as they are in the third row, junction of third row and third column of the right-hand side matrix. So that implies what? A33 should be equal to minus A33. So this implies what? This implies 2A33 is equal to 0. This implies A33 is equal to 0. So what we see, dear students, that A11 equal to 0, A22 equal to 0, A33 is equal to 0. That means what? This matrix, original matrix A, if you see all these elements A11, A22 and A33 is 0. What is this element? A11, A22, A33. That is the diagonal elements, na? That is what we know as a diagonal elements, correct? So what we establish this property that all the diagonal elements of a skew-symmetric matrix are 0. That means what we get, dear students, this matrix A is actually now transforming to. So what we are getting this matrix A now finally is that is equal to 0, then A12, A13, A21, 0, A23, A31, A32, 0. So what we get, dear students, the diagonal elements is 0. We establish this thing. And that's why if you see the example of a skew-symmetric matrix, what I started with, that is 0EF, minus E0G, and minus F minus G0, if you see here the diagonal elements are 0. Correct, no? So this is an important property that all the diagonal elements of a skew-symmetric matrix are 0. Now, dear students, we are going to go through the next few properties. The next property what I'm going to tell is that, okay, is that for any square matrix A of real numbers, both the following holds true. What are those? You know, A plus A transpose is a symmetric matrix and A minus A transpose is a skew-symmetric matrix. Let us, deep dive into it. Let us understand this thing in a little, elaborative manner. What we see, dear students, here is that, let me read it once more as you see the note here. It says that for any square matrix A of real numbers, both the following holds true. First one, it says that A plus A transpose is a symmetric matrix and A minus A transpose is a skew-symmetric matrix. Let us establish that so that you have a very clear idea why Sir is saying so. Now, A plus A transpose is a symmetric matrix. So how to establish that one? Let me use a different color. So now we are concentrating on this. So A plus A transpose, let's make A plus A transpose transpose. Okay. So what we know that A plus A transpose, if you recall from the properties of the transpose of a matrix, dear students, A plus A transpose should be A transpose plus A transpose transpose. Correct, no? So this implies what? This implies A plus A transpose transpose is equal to A transpose plus, we know from another property of the transpose of a matrix, transpose of the transpose of a matrix is the original matrix. That means A transpose transpose is nothing but A. So what we get, dear students, that A plus A transpose its transpose, what we see is that A plus A transpose. That means what? If you consider that A plus A transpose is a matrix, then its transpose is equal to A plus A transpose, that is the same matrix. Means, what I want to say is that if we assume let A plus A transpose, we are writing it as equal to B. Then what we are going to conclude from here, this implies B transpose is equal to B now. If B transpose is equal to B, then what we can conclude? This implies B is a symmetric matrix. And but what is B? B is nothing but A plus A transpose B. That is A plus A transpose is a symmetric matrix. Symmetric matrix. I hope you got a very clear idea. Now the next one is that what we are going to discuss, dear students, is that A minus A transpose is a skew-symmetric matrix. Let us establish that. And that's why I'm using a different color, blue pen. So what I'm going to do now, we are going to find that A minus A transpose. So that is equal to what, dear students? That is equal to A transpose minus A transpose. Correct or not? That is, we are getting from the properties of the transpose. Correct? You know, more elaborately, I can write like this. You know, more elaborately, more elaborated manner. What I can write is that this I can write A plus of minus 1 into A transpose. Correct? So this is equal to what? This is equal to A transpose plus minus 1 into A transpose. This we are getting from the properties of the transpose of a matrix. That A plus B transpose is equal to A transpose plus B transpose. Now, this A transpose to as it is. And you know, dear students, there is a property we have learned. K into A transpose. K transpose is equal to K into A transpose. So that is equal to what? That is plus minus 1 into A transpose. Let me write properly. Minus 1 into A transpose. So A transpose, correct, na? Sorry, this should be transpose here. This should be transpose here. So A transpose. So this equal to what, dear students? That is equal to, we get A transpose minus of A transpose. Now, what is A transpose? We learned that is nothing but the original matrix A. So that is equal to A transpose minus A. That is equal to what? Minus of A plus, minus of A minus A transpose. So what we see, this all we can see from here is that, so this implies here, all you can write is that A minus A transpose, this implies A minus A transpose. This implies all these things I can write, no? A transpose. This implies A minus A transpose. This implies A minus A transpose. This implies A minus A transpose. Now, let us assume, dear students, that A minus A transpose is equal to C. So let A minus A transpose is equal to C. Then what we are going to get out of here? This implies C transpose is equal to minus C. Now, dear students, recall the property of a skew-symmetric matrix. If C transpose is equal to C, that means C is a skew-symmetric matrix, correct now? So then what we are going to say from here is that this implies C, that is A minus A transpose, is a skew-symmetric matrix. Skew-symmetric matrix. If you have any smallest doubt, dear students, please feel free to me. So this is one important property we have established. What is that? For any square matrix A of real numbers, we can express A plus A transpose as a symmetric matrix and A minus A transpose as a skew-symmetric matrix. Now, the next important property, that is a very important property. Okay, what we can write is that for any square matrix A, we can, write these two statements, and I'm going to establish it in the next page, the proof, and it's a very important proof. And you need to understand the little bit of mathematical logic here very properly. So if you look into the first one, dear students, is that for any square matrix A, you can write the following manner: A is equal to half of A plus A transpose plus half of A minus A transpose, because half of A transpose and half of minus A transpose will get cancelled, na? So finally we will land up with half A plus half A, which is A. So that means what I'm saying is that if you do a calculation here, what you will get? Half A plus half of A transpose plus half A minus half of A transpose. Now if you see half of A transpose minus of half of A transpose, that get cancelled. So what half of A here? So what we'll end up with, half of A, let me write properly so that there is no confusion. Half of A minus half of A transpose. So if you see half of A transpose minus half A transpose get cancelled, and we are finally land up with half A plus half A. That is actually A. Correct, no, dear students? So in the bracket, what I say is that, so what I'm saying is that any square matrix you can express as a half of A plus A transpose plus half of A minus A transpose. And that expression leads to a very important conclusion, what I mentioned in the next one. It says that any square matrix can be expressed as a sum of symmetric matrix and a skew-symmetric matrix uniquely. And uniquely is a very important word here, and we will see why it is so. And I am going to establish this property with derivation. So in the next few minutes, dear students, you will find a derivation from me to establish this statement that any square matrix can be expressed as a sum of symmetric matrix and a skew-symmetric matrix uniquely. How? Let me show you. So first of all, dear students, let A be a square, symmetric matrix. Let me write a different color, okay? Let A be a square matrix such that A is equal to B plus C. That means you are expressing A as B plus C, in which I'm just giving this as the equation 1, in which B is a symmetric matrix, in which B is a symmetric matrix. That implies what? From the definition of symmetric matrix, B transpose, I'm writing here transpose like this, B transpose is equal to B. So this we give an equation 2. And C is a skew-symmetric matrix. C is a skew-symmetric matrix. That implies what? That implies, from the definition of skew-symmetric matrix, C transpose is equal to minus C. So this we give as equation 3. So dear students, so far what we have done, we have expressed A as a sum of two matrices in which one is a symmetric matrix, which is B, and another one is a skew-symmetric matrix, that is C. That means A has been expressed as B plus C, in which B is a symmetric matrix and C is a skew-symmetric matrix. Correct? Now what I am going to do is that I am going to make a transpose of both the matrices in both the sides of the equation A. So from equation 1, what we are going to get, this implies A transpose should be equal to B plus C transpose. Not a big deal. So this implies what? This implies A transpose is equal to, from the properties of the transpose of a matrix, dear students, B plus C transpose is equal to B transpose plus C transpose. Now, by means of the equation 2, what we can write? We can write in the right hand side B transpose is equal to B and C transpose is equal to minus C. So what we get, let's give this as equation 4. So the equation 1, what we get, dear students, let me use a little different color. In the equation 1, we get A is equal to B plus C. And equation 4, we get A transpose is equal to B minus C. Now let's concentrate on these two equations, equation 1 and equation 4. Let's add both sides of equation 1 and equation 4. What we are going to get? If we add both sides of the equation 1 and equation 4, I am writing this as symbolically 1 plus 4. That implies what? We will get A plus A transpose is equal to B plus C plus B minus C, that is equal to 2B. That means what? We get 2B equal to A plus A transpose. So that implies B is equal to 1 by 2 into A plus A transpose. So this is the matrix B, what we achieved. And B is a symmetric matrix. We have achieved it. We can, we already assume that B is a symmetric matrix and we are using its property. Not only that, if you make a transpose of B transpose, you will get the same matrix B. So we assume B is a symmetric matrix and we found the value of B in terms of A. What is that? B is equal to 1 by 2 into A plus A transpose. Now in the similar manner, we can find the matrix C in terms of A. How? We are going to do, equation 1 minus equation 4 of both the sides. What we are going to get? Left hand side we will get A minus A transpose. And then right hand side we are going to get, it is B plus C minus B minus of minus C, that is plus C. That is 2C. This implies what we are going to get, C is equal to half of A minus A transpose. Correct, dear students? So what we are able to do, we are able to express the matrix C in terms of A, where B is a symmetric matrix and C is a skew-symmetric matrix. So what we have achieved so far, we have achieved, what we can write is that, so we are able to express A as, so what we can write is that, so we are able to express A as 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose, in which the first matrix, let me use a different color, dear students. In the first matrix, what you see, this one is a symmetric one this is a symmetric matrix, and the next one is a skew-symmetric matrix. So now the point is that if you see that when I mentioned this statement that any square matrix can be expressed as a sum of a symmetric matrix and a skew-symmetric matrix uniquely. Expression, so we are done, that we are able to express A is equal to half of A plus A transpose plus half of A minus A transpose. So we are able to establish the first part. But how to establish the second part, that this is the unique way of representation? How come we can ensure that it is not possible to express that matrix A as a sum of a symmetric and skew-symmetric matrix in a two different manner? And when to establish this kind of proof, we take the root of contradiction. That means to prove that that it is not a unique manner. So what we are going to do? Let me use a different color, dear students. Let me use this color. If possible, to prove the uniqueness, this we are going to achieve. This we are going to establish. Let, if possible, we are able to express A is equal to P plus Q, in which P is a symmetric matrix. P is a, let me write here, in which P is a symmetric matrix. Q is a skew-symmetric matrix. Skew-symmetric matrix. And third one is that P is not equal to half of A plus A transpose, because uniquely, if possible, that we are able to express in different manner. P is not equal to half of A plus A transpose, and Q is not equal to half of A minus A transpose. Correct, now? If possible. And why I wrote, dear students, that P is not equal to half of A plus A transpose, because we are assuming that some other way also we can represent A, okay, in which A is not equal to half of A plus A transpose, because one way we already established by means of this, if you see. And as P is a symmetric matrix, so what we can say, that implies P transpose is equal to P. And as we see, Q is a skew-symmetric matrix, that means Q transpose is equal to minus Q. Now what we are going to do, dear students, that A is equal to P plus Q. So from here, what we can write? We can write that A transpose is equal to P plus Q transpose. This implies what? This implies A transpose is equal to P transpose plus Q transpose. That is, we are getting from the transpose of a matrix, that property. So as P is a symmetric matrix, so we can write A transpose is equal to P as we already wrote here, na, P transpose equal to P and Q transpose is equal to minus Q. So what we get, dear students? We get A is equal to P plus Q. We can give this as equation 1. And we get A transpose is equal to P minus Q. That is equation 2. Now what we are going to get is that if we add both sides of the equation 1 and equation 2, then what we are going to get? We are going to get P is equal to, after simplification, because A plus A transpose would be equal to P plus Q plus P minus Q. That means I can write also so that there will be no confusion. A plus A transpose, that is equal to P plus Q plus P minus Q. This implies what? 2P is equal to A plus A transpose. That implies P is equal to half of A plus A transpose. A transpose, which contradict to the assumption that P is not equal to half into A plus A transpose. Not dear students. If you see, for uniqueness, we assume that P is not equal to half of A plus A transpose. But what we'll end up with this assumption, we'll end up with that P is equal to half of A plus A transpose. So what we can write? We can write that which contradict to the fact that which contradict to the fact that P is not equal to half of A plus A transpose. So that is a contradiction. That means what? It is uniqueness hold true. No other way you can express A as a sum of two matrices where there are two different ways. One is symmetric and one is skew-symmetric, but in two different ways. Not possible. In the similar manner, what we can do is that if we make equation 1 minus equation 2, that implies what? That implies A minus A transpose. That is equal to what? That is equal to, we get P plus Q minus of P minus Q. Now if you simplify, dear students, what we get? 2Q is equal to A minus A transpose. That implies Q is equal to half of A minus A transpose. That again contradict to the fact, to our assumption, that Q is not equal to half of A minus A transpose. That was our assumption, no? But what we'll end up with? We actually contradict that assumption. Okay? So what we can say is that which contradict to the assumption and fact in this context is same. Which contradict to the fact, assumption, statement, all are synonym in this context, that Q is not equal to half of A minus A transpose. So what it says that hence we conclude that matrix A, any square matrix A, can be expressed as a sum of a symmetric and skew-symmetric matrix uniquely. Hence we conclude that, hence what I can write, I can use a different color. Hence we conclude that, what we can conclude? We can conclude whatever I wrote earlier. Any square matrix can be any square matrix can be expressed as a sum of a symmetric and skew-symmetric matrix uniquely. That we are able to establish it, dear students. Now, dear students, so there is a, the question generally come, most of the time, you need to express a matrix, as a sum of a symmetric and skew-symmetric matrix. Very classical question generally comes. So I would like to touch base on that question. Okay. So one such example, I'm just going to place in front of you, and I will tell you the exact way of performing that kind of question. Okay. So what is that? So let me first keep the question, and then I will explain you how to perform that kind of question. So let me first, place the question. As you see, dear students, here the question is that express the matrix B as a sum of a symmetric and skew-symmetric matrix. The steps I am going to tell you. It is a very simple step, effective step. So what you need to do first, dear students? First, you need to go through the statement what I said in my previous slide, is that we need to first write that B is equal to half of B plus B transpose plus half of B minus B transpose. Now, in this expression, what we can say, dear students, this first part is a symmetric matrix. This first part is a symmetric matrix. And the second part, dear student, it is a skew-symmetric matrix. That we have established. So what is our task? Our task is to find B transpose, then add this divided by 2. That will be a symmetric matrix. And then we'll find B minus B transpose, and then divided by 2. That means scalar multiplication with 1 by 2. That will be a skew-symmetric matrix. That's all we need to do. So for that, what you need to find? You need to find B transpose. And if you find B transpose, dear students, it is quite simple. You can find the B transpose something like this. If B is the matrix, so let me make a consistent way of writing. So what I'm going to write is that, though T you can write like this, but let's follow a consistency. So B transpose, sorry, let me use the same color. So B transpose and B minus B transpose. So if B is this matrix, so B transpose, you can find it out. We have done today. What is transpose? Row become column, column become row. Quick way of recapping. What is the first row of the original matrix B? 2 minus 2 minus 4. That becomes the first column of the transpose matrix 2 minus 2 minus 4. In the similar manner, the other also happened. Now, as we find B and B transpose, now we can find half of B plus B transpose. Correct or not? So if you find half of B plus B transpose, you will get something like this. So that means what we are going to get is that half of B plus B transpose, you will get a matrix something like this. Okay. So from here, what you are going to get is that half of B plus B transpose will be something like this. Correct, not dear students? You can do it actually. It is pretty simple. You need to add the individual terms and then divide it by, and 1 by 2 is already there. Okay. you know the addition of two matrices. And in the similar manner, and if you little simplify this thing, what you are going to get, dear students, you will get a matrix something like this. You will get a matrix like this. That is a half of B plus B transpose. Now, what we're going to find, dear students, is that we are going to find half of B minus B transpose. In the same manner, you can find B minus B transpose, half of B minus B transpose. How? Let me show you. So you will get half of B minus B transpose is something like this. So now our matrix, what it will be addition of these two matrices. So this matrix, what you see, dear students, that half of B plus D B transpose, this is a symmetric matrix. Okay. And what you see, half of B minus B transpose, that is a skew-symmetric matrix. Correct, not, dear students? So what we established here is that we are able to establish that it is the given matrix as a sum of a symmetric and skew-symmetric matrix. And in fact, if you assume this, half of B plus B transpose, if you make a transpose, you will get the, the same matrix. So finally, what we get? Finally, we are able to establish that given matrix A, what is the matrix is actually given to us, is actually expressed as a sum of a symmetric and skew-symmetric matrix, which is the matrix B. Correct? So let me show you finally this thing, that what we are finally able to achieve. We are able to achieve this thing, that the given matrix B, which you see in the right hand side, is actually expressed as a sum of a symmetric and skew-symmetric matrix. This is a symmetric matrix. This is a symmetric matrix, which is nothing but 1 by 2 into B plus B transpose. And if you see, dear students, this is skew-symmetric matrix. This is skew-symmetric matrix, which is nothing but half of B minus B transpose. So this is a very common question which generally comes. So how to find it out? Let me tell you once more before we conclude the class. First thing, dear students, if the question is that express the matrix B as a sum of a symmetric and skew-symmetric matrix, our first step should be to express that matrix B as a half of B plus B transpose plus half of B minus B transpose. That should be our first step. After that, we will compute B transpose as we have done it here. Then we will find that half of B plus B transpose, we will get it here. And then you can prove it that is a symmetric matrix. Means what you can do is that you take a half of B plus B transpose, complete transpose. Okay, and you will get, you need to show that what you are getting is that half of B plus B transpose. That we have done it today, and you can establish that here. In the similar manner, next step what you need to do is that you need to find the value of B minus half of B minus B transpose, and you will get this thing. And what you can establish is that half of B minus B transpose, its complete transpose is nothing but half of B minus B transpose that we have established it today. Once you are done, so that means you can conclude now that half of B plus B transpose is a symmetric matrix and half of B minus B transpose is a skew-symmetric matrix. After what is left? After that is just addition. Okay, from where we are getting this addition? From our this assumption, this one, dear students, correct? If we give this as equation 1, from this equation 1 only you can write this thing, that from equation 1 it follows this thing, that you can add the original matrix B, which is given to us as a sum of a symmetric matrix, which is this is the symmetric matrix and this is the skew-symmetric matrix. I hope you get a very clear idea. Now, in the next class, dear students, we will discuss about the inverse of a matrix, invertible matrix, under what condition we can find the inverse of a matrix. And before I conclude, dear students, so please, always log into, www.KonarClasses.com. I'll always suggest you to log into www.KonarClasses.com and look for, and what I can say, and look for, first one is that video lectures, second one is that DPPs, that stands for daily practice problems. Then go for the PTs, that is known for practice tests. Then you can go for that UTs, that is called unit tests. Then you can go for MDTs, that is known as module tests. Then finally you can go for MTs, that is known as mock tests. Okay. For any assistance in future, you can always reach to us our email. Our email ID is at contact@KonarClasses.com and our WhatsApp number is 80950100670. With this, I would like to conclude the class, dear students, and our next class is day after tomorrow, in which we'll start discussing the inverse of a matrix. Thank you very much. Take care.
Thank you, sir.
Thank you, sir.
Thank you.